In this session, I'd like to explain the evolution of our stars using the T-law planes. So in these figures, all the information are combined. The zones, nuclear burnings, and also evolutionary paths. So when we consider the evolution of stars, initially the density and temperature of the central part of the star is really low. Then density and temperature is increasing. And first it's moving up. We cannot say that at this point is a stars. Temperature and density is increasing. And finally, temperature and density come to this point. Nuclear burning starts by burning the hydrogens. And this is a vast nuclear burning threshold. It takes a really long time. Star consumed a huge number of the hydrogens. And at the centers, quantity of the hydrogen is decreasing. Finally, it's consumed most of the hydrogen. And the heliums cannot burn at this temperature. Helium needs a higher temperature to be burned. Once most of the hydrogen is converted to the heliums, these stars cannot burn the hydrogen anymore, and the temperature and the density is increasing again. So this is the end stage of the main sequence stars. And increasing, and they cross the boundary between the degeneracy pressure and the ideal gas. Then once this evolutionary path meets this point, inside of the degeneracy pressures, evolutionary paths have to follow these lines. Yes, and the temperature is decreasing. We call this is a white dwarf. So I explained this one. Evolution of low mass stars. Stars form in the gaseous clouds where density and temperature are low. Stars contract and heat up the central point. Temperature and pressure increases. When the central point crosses the first nuclear burning threshold, hydrogen burning starts. So it takes a really long time. Thermal equilibrium is maintained for a very long time. So in this case, luminosity is equal to the generation of the energy at the central point, nuclear reaction. So hydrogen is exhausted, the core contract and heat up again. Low mass stars, degeneracy pressure dominant, contraction. Compact star made of the heliums. High mass stars, density increases until the next nuclear burning, helium burning, then carbon is generated at the centers. So degeneracy pressure dominant, contraction. In this case, the compact star composed of the carbon and the oxygen are forming. When the high mass stars is close to the main sequence stars, density increases until the next nuclear burning. So triple alpha reaction is happening here. At the central regions, helium is converted to the carbon. So center of these stars, main composition becomes carbon or oxygen. They cross the boundary between the degeneracy and the ideal gas. Then this star is moving to this direction, becomes a white dwarf. So compact stars inside the degeneracy region we call the white dwarf. Then star with a Chandrasekhar mass. Dividing line between the stars that becomes compact stars and those that remain in the ideal gas state. Actually, this is close to the carbon burning. This is thermally unstable. This ends up with a type 1 supernova explosions. So when the mass exactly equal to the Chandrasekhar mass on this line, triple alpha reaction, the helium is burning at this point and the carbon burnings, and it ends up the supernova explosion. We call it this is type 1 supernova explosions. So evolution of the massive stars, more massive than the Chandrasekhar mass. So we should follow these lines. So density and temperature is increasing at the centers. Then cross this line. Hydrogen is burning by the CNO cycles. And if the hydrogen is consumed at the centers, then next nuclear burning starts. Helium is start to burn to produce the carbon. And once the helium is consumed, then temperature and density is increasing. And come to the carbon burning. Now at the centers, carbon start to be burned. And if the carbon is consumed, then temperature is increasing. And next burning of the oxygen starts. And a series of the nuclear reaction is happening at the centers in the heavy mass of the stars. So evolution of the massive stars. Helium is exhausted. The core contracts and the heat up gains. And the carbon burning, the oxygen burns. Series of the nuclear reaction is happening at the center of massive stars. Silicon burning. And the iron photo disintegration is happening because iron is the most stable element in the universe. Then iron photo disintegration consumes a huge amount of the energies. This is highly unstable. Then the central region is a collapse at the centers. End up with a catastrophe event, type 2 supernova explosion. So I'd like to explain the late evolutionary stage. For any given point M within a star, we have a value of the local temperatures and the local densities. At the central point, of course, this is the highest temperature, the highest densities. If you consider the structure of the stars, outer regions as a lower temperatures and the lower densities. The lowest density is go to the zero. Zero density is corresponds to the surface of the stars. If you follow this, you can find that the density at the midpoint of the stars. We can find the density at each point inside of the stars. In the case of the star of the A, at the center of the stars, hydrogen is burning. In the outer region, stable hydrogen exists. So in the main sequence stars, at the very center, hydrogen is converted to the helium. So nuclear burning occurs at the centers, but most of the atmospheres, stable hydrogen exists. This is the main sequence task. If the hydrogen is converted to the helium's central pressure and density is increasing. So in the stage of the B, this is the central point of the stars. So at the central point, actually the hydrogen is converted to the helium. So at the central point is a helium core exists. And then outer regions. At some point, density is decreasing. At this point, hydrogen is burning. So from the outer regions, hydrogen burning shell, hydrogen is converted to helium. So on this shell, hydrogen is burning. And out we could discover stable hydrogen. So by following these lines, you could understand structure of a stars. At the center of this stars, stable helium you could find. At the middle point, you can find the hydrogen burning shell. Outer region, you can find the stable hydrogen atmospheres. So this corresponds to the red giant. Hydrogen depleted in the cores, so it's helium cores. So in the red giant, total energy has to be conserved using the virial serums. Total internal energy should be conserved, and the total potential energy should be conserved. So using these virial serums, total conservation of the potential energy. So as I explained, central region is collapse. Contraction of the core must be accompanied by the expansion of the envelope. Central region is a contract, so this means the gravitational potential energy is increasing at the centers. Total potential energy has to be conserved. Envelope has to decrease potential energy. So envelope has to expand it. And also heating up of the cores, then temperature is increasing. But also we discovered internal energy has to be conserved. So heating up the core has to be accompanied by the cooling down of the envelope. Temperature of the envelope is decreasing. So this means the color of the envelope is changing to the red because of the decrease of the temperature. Last one is a C, structure of the C. So at the centers, we have iron cores. This is iron cores. And the silicon burning shells. And the oxygen burning shell. And the carbon burning shell. A number of the shell, actually different element is burning. Hydrogen burning, helium burning shell, carbon burning shell, oxygen burning shell, and the silicon burning shell we discovered. It's like a layers, like onions. The iron is the most stable element. Iron cannot generate energy. So iron contracts to increase the temperatures. Iron core contracts. Temperature of the core increases, and the core is disintegrated by the energetic photons. So iron is disintegrated, the heliums. These reactions need a huge amount of energy. The loss of the high energy results in the rapid collapse of the cores. Further collapsion of the core is leading to the increase in the temperature. Temperature is increasing. This helium is also break into the proton and the neutrons. This is also need energy, 24 mega electron volt. They contract further. Then protons start capture the electron to produce the neutrons. At the centers, main composition becomes the neutrons. So finally, degeneracy pressure of the neutrons stop the collapse. So this is the formation of the neutron cores at the centers of this heavy mass of stars. So supernovas, collapse of the core release the gravitational energy. During the formation of the neutrons, by the capturing the electron of the protons, huge amount of the neutrino is forming. And neutrino leaves the core with the energy. Neutrino are absorbed by the envelope. This ends up with the explosion of the envelope. We could observe this event as a supernova explosion. Okay, this is the end of this session.